We're going to take a look right now at an important concept that we'll be using throughout this semester involving significant figures and how we evaluate significant figures when we're doing calculations. So before we begin the discussion, and I should mention also that this information is found in your textbooks in section 2.2 and 2.3. Before I begin a discussion of significant figures, we first of all need to recognize that there are two classes or types of numbers. There are measured numbers, data that we collect by making measurements using instruments, and these numbers will inherently contain uncertainty with them. Sig figs apply to all measured values. There are also another set of numbers, smaller category, known as exact numbers. They do not contain uncertainty and sig figs do not apply to them. Example with exact numbers, because that's easier to deal with, and then we'll come back to measured numbers. But looking at exact numbers, there are two basic categories of exact numbers. There are counting numbers, like how many objects are present in a container, such as 12 eggs in a carton. You can open up the container, count the number of eggs there. There's no uncertainty about it because they're discrete, whole, separate objects. So counting numbers are an exact count, contain no uncertainty. Sig figs do not apply whenever you're counting number of objects or people in a classroom per se. The other type of exact numbers that we encounter more often in chemistry is defined relationships. For example, in the metric system we've already looked at, 10 decimeters is exactly equal to 1 meter. That's a defined relationship, exact. No uncertainty, sig figs do not apply. This is also true of, say, the English system of measurement. All systems of measurement that have relationships built into that system. For example, 12 inches is equal to 1 foot. That is an exact relationship, defined relationship. Sig figs, abbreviated SF, don't apply. But most of the time in science, we're making measurements, and those numbers inherently contain uncertainty. And let's use this little drawing here as an illustration of that. And what I've tried to draw up on the board is an example of a metric rule. So I've blown it up, and we're going to measure an object using this metric rule drawing, this red object that we've placed up against the metric rule. Notice the information in the upper left-hand corner tells you that the whole numbers are centimeter values. You see that it's divided into whole number divisions, 1 centimeter, 2 centimeters, and so on. The jagged edge means I haven't continued the drawing. And then we see that each centimeter distance is further subdivided into smaller divisions. And the way we figure out the meaning of those divisions is to take a look at the numbers, 1 centimeter, 2 centimeter, and count how many divisions are separating those two distances. So I'm counting 1, 2, 3, 4, 5. So right in the middle, the hash mark is a little larger, indicating, or longer, indicating we're halfway between 1 centimeter and 2 centimeter. So right here, 1.5, and then continuing on, 1, 2, 6, 7, 8, 9, 10. So I'm looking here and I see that this division is a 10 division separation between 1 centimeter and 2 centimeters. So each little line, 1 divided by 10, is a tenth of a centimeter. And I'm just going to double check that. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2 centimeters. So in other words, when you're looking at an instrument, the responsibility is on you to make sure that you can determine what the distance is represented by the smallest hash marks. You take the distance total between the numbers, divide it by the number of hash marks, and come up with your value. Each hash mark is 1/10 of a centimeter. We're now ready to make a measurement of the length of this object, red object, placed up against the metric rule. It's clear to me as I look at this object that the length is at least 1 centimeter, but less than 2 centimeters. Past the 1 centimeter line, but less than 2 centimeters. I can also see as I count the hash marks, each hash mark being 1/10 of a centimeter, that this object is at least 1.4 centimeters in length, but it is not quite 1.5 centimeters. But I cannot stop my answer right there. This is a measured value. The last digit that you write, the last significant digit, is the place that you say you are uncertain in the reading of the measurement. And it's clear to me, and I hope to you from this drawing, that this object is at least 1.4, and we'll put that unit there. Of course, it is so important that we have a unit with a number so we understand the meaning of that value, what it applies to. It is an incorrect number of significant figures to write this as 1.4 centimeters. Why is that? Because we are not uncertain about the 4. So what we have to do is estimate between the 1.4 and the 1.5 centimeters, take that distance and mentally divide it into 10 smaller fractions in our mind and estimate. That's where the uncertainty is coming in. Now I'm looking at this length myself, and I think that it is less than halfway between 1.4 and 1.5 centimeters. I'm kind of estimating here, and I would probably report this number as 1.43 centimeters for the distance or length of this object. But if you reported 1.44 centimeters, I wouldn't mark you wrong. There is some uncertainty there. So we generally understand it to be plus or minus 1 in the place of uncertainty, which in this instance is the hundredths place. Plus or minus 1 in the place of uncertainty, which means the true value could be anywhere from 1.44 centimeters, adding 1 to the uncertain 3-digit in the hundredths place, all the way down to 1.42 centimeters. We don't actually know what the true length is. Our uncertainty is in the hundredths place, and it's understood to be plus or minus 1 in the place of uncertainty, last significant digit written. We expect that the true value lies in that range. So what if we had a situation, this is often a confusing point for students, where we're measuring an object that appears to have a length that falls exactly on a hash line. Again, it's important to square our object flush with the end of the metric rule so they align. And let me just add some dots here so it just kind of stands out a little bit more. Right, so I'm trying to draw the end of this second object flush exactly on a hash mark. How would we express that length? So again, we're looking at the object, the instrument, and counting here. It looks like the object. Here is our 1.5 centimeter length, 1.5, 1.6, 1.7, 1.8. So it looks like the object has a length of 1.8 centimeters. But again, you can't leave the value like that. This is a measurement with the incorrect number of significant figures. expressing the incorrect place of uncertainty. We are certain that it is 1.8 centimeters. It is exactly, to our eye, as best as we can see, on the 1.8 line. So we need to add a 0 there to indicate exactly on the line, not extending past at all, and we are reading this value as 1.80 centimeters. Notice each of these numbers has 3 sig figs to it. Each of the values has 3 sig figs, which leads us to a question of how do you count sig figs in a measurement? So you need to memorize table 2.2 in your text, which gives rules for counting significant figures in measured numbers. Note, all non-zero numbers are significant. That's an important and easy rule to memorize. All non-zero numbers in a measured value are significant. The only question is, what's up with the zeros in a measured number? They may or they may not be significant. So how do you determine whether a 0 in a number is or is not significant? The rules on table 2.2 explain that. I'd like to just illustrate those rules with examples and state the rule as we go through. So our first measured value, notice all of these measurements have a unit attached to them. So we know these are all measurements that have been made and contain uncertainty. So here's the measurement. We're going to count the number of significant figures in that measurement. Our first measurement has 3 non-zero numbers. All non-zero numbers are significant, so the number of significant figures in this first measurement is 3. 3 significant figures. And now all the remaining values are numbers that have zeros associated with them. So let's take a look at our first example. Whenever you have a measured number where zeros are falling between 2 non-zero numbers, those zeros are automatically significant. So this second reading has 4 significant figures. The 2 zeros between the non-zero numbers are significant. Our next example involves a 0 that follows a non-zero number and is to the right of a decimal point. So a 0 coming after a non-zero number and to the right of a decimal point. This is a significant digit. This 0 is significant. Of course, the 2 is as well. So this measured value has 2 sig figs. Now let's take a look at a number written in scientific or exponential notation. The coefficient portion of the number is where you evaluate the number of sig figs. You do not count the exponent on 10 as part of the sig fig count. So looking at this number, the coefficient, the 0 comes after a non-zero number to the right of a decimal point. So that 0 is a significant digit, and I'm counting 1, 2, 3 sig figs in this 4.30 times 10 to the 4th decigram value containing 3 sig figs relating to the coefficient of the number. Let's move to our next example, a little more complicated, more zeros involved, trying to build our understanding and apply it. The first thing we notice is that this number begins with zeros. There are no non-zero numbers at the front of this value. It's beginning with what we call leading zeros. These leading zeros are not significant. Zeros that appear before a non-zero number are not part of the uncertainty of the measurement. They're just indicating the magnitude or size of the value. So these leading zeros, not significant. The zero that comes between the two non-zero numbers is significant. And the zero at the very end of the number, coming after a non-zero number and to the right of the decimal point, is also significant. So looking at this value, I'm seeing 1, 2, 3, 4 significant figures in the value. 4 sig figs. The last example is the one, you see that kind of a uncertain face, is the most difficult and trickiest of all. This is a number which ends in zeros to the left of an implied decimal point. So a decimal point is not showing here, it is implied, and the question is, are these zeros significant or not? Where is the actual uncertainty in this measurement? Is it in the ones place? Is it in the tens place? Is it in the hundreds place? Or thousands place? It's not clear. Right? So this example to me is a case of we don't know how many sig figs this number has. Therefore, you cannot express it in this form. You have to express it in a form that clearly indicates how many significant figures are present in the number. If all of the digits are significant, in other words, both of the zeros, all you have to do is put a decimal point in that value and add the unit. You are now saying that this value has 4 sig figs to it. So I'll give you a moment to just look at that and think about that. If the number does not have 4 sig figs to it, in other words, let's say the uncertainty in the reading is in the tens place. This number only has 3 significant figures. Then you have no choice but to put this into scientific notation. So I'm moving that decimal place over to the right 3 places. So times 10 to the third. Remember, proper scientific notation is always one non-zero number followed by the decimal point. The exponent on 10 is the number of places you have to move the decimal point in order to have a single non-zero number followed by the decimal point. And notice the uncertainty here is in the tens place, so I am not including that last zero. This number has 3 sig figs. Let me put that unit in as well. 3 sig figs, indicating it's 1,200 liters, but the uncertainty is in the tens place, not the ones place. So you must put it into scientific notation if you're expressing it with either 3 sig figs, or 2 sig figs, or 1 sig fig. Notice if it was expressed with 2 sig figs, I would just put 1.2 times 10 to the third liters, expressing that with 2 sig figs. Let's take a look now at section 2.3, which involves how we evaluate sig figs in an answer from a numerical calculation. And again, there are 2 different types of calculations we'll be doing, either multiplication or division, and second category, addition or subtraction. So multiplication, division versus addition and subtraction. There are 2 different principles involved with this. Notice with multiplication, division, your final answer can have no more significant figures than the smallest number of sig figs contained in any number used in the calculation. So notice the example that I have up on the board. This is an example where we would be measuring the length, the width, and the height of an object, and then calculating the volume of the object based on the principle that volume equals length times width times height. So measurements are made, and notice different types of instruments are used to make the measurement, right, with different precision. This first reading has uncertainty in the tenths place, but these last two readings correlate with this sort of instrument that we used in our first example and have uncertainty in the hundredth of a centimeter place. All right, so I do this calculation. My calculator is showing this answer, and you can pause and double check. I always double check my calculation and make sure, okay, and I can triple check it right here with you, that when I do this mathematical operation, right, I get the answer that's showing up on the board. And I have now triple checked it. The question is, how many sig figs should that answer be expressed to? Where is the uncertainty in the reading? Calculators do not understand sig figs. Their operators understand. You understand. I understand. We bring that knowledge to this calculation. Using the rules that we just looked at above and quickly evaluating the number of sig figs in each of these measurements, I'm counting 3 sig figs for the first measurement. That 0 that we encounter is following a non-zero number to the right of the decimal point, and it is significant. The second measurement, leading 0, is not significant. Any zeros that come before a non-zero number, not significant, and this has 2 sig figs. Last value, last measurement, this 0 falling between 2 non-zero numbers is significant, so this last measurement has 4 sig figs. Therefore, according to the principle, our final answer can have no more significant figures than the smallest number of sig figs in any number used in the calculation. That means our answer can have no more than 2 sig figs, which means the uncertainty of this measurement is in the tens place. So how are we going to express this properly? We have no choice but to put it into scientific notation. We certainly can't write 97. By the way, notice the unit. The unit is centimeters cubed, which illustrates dimensional analysis. You have to operate on the number and its corresponding unit. So centimeter times centimeter times centimeter is a centimeter cubed, a cubic centimeter, or cc. We have to express this number in scientific notation to indicate that it has 2 sig figs. Since what comes after our place of uncertainty is less than exactly 5, we're going to use rounding rules and write this number as 970 with 2 sig figs. That means I will express the measurement as 9.7 times 10 to the second centimeters cubed. So our final answer, written in scientific notation with 2 sig figs to it. The rules for addition and subtraction are different. It is not a case where you count the smallest number of sig figs in any value. That is not the rules that you're looking at. Here, your final answer must be rounded to the place where uncertainty first begins in any value. I'm going to change this number just a minute to illustrate that better. All right? Well, maybe not. Just trying to think here of what would help you. Right, so maybe we do an addition and we do 1, 1. Right? So if we add these two numbers up, gram amounts, add them up on the calculator, I see when I add them up 3.050 plus 1,124.2. I get on my calculator a final answer of 1,127.250. But these digits are not all significant. Now you cannot use this rule. You cannot use the multiplication division rule. 4 sig figs, 5 sig figs, our answer should have no more than 4 sig figs. That's a common but incorrect error. Instead, the final answer must be rounded to the place where uncertainty first begins in any of the numbers being added. So in our first value, uncertainty begins in the 1,000th place, making sure you see that decimal point clearly. In the 1,000th place, in our second number, uncertainty begins in the 10th place. Our final answer has to be rounded to the 10th place. That's where uncertainty is first beginning in the measured values we are adding. We encounter it first in the 10th place. So I have to use rounding rules to express this answer in the 10th place. And since what comes after the place of uncertainty is exactly 5, we're going to round that 2 up to 3 and report our final answer as 1,127.3 grams. Notice that is a value with 5 sig figs, even though 4 sig figs was a smaller number of sig figs used in the addition. You do not count sig figs in the numbers being added. You do not do that. Instead, you evaluate where uncertainty first begins in any of the numbers being added together. Notice it is very helpful to align those decimal points as you're learning this principle to help your eye visualize where uncertainty first begins.